So much like we covered the FabricPath control plane, there are certainly very important data plane elements to FabricPath. The first is the MAC table. So FabricPath keeps a MAC table, and I'll go into more detail in a subsequent slide. And essentially, the hardware performs MAC lookups at the CE or FabricPath edge only. FabricPath also has a switch table, which we saw earlier, and the hardware performs destination switch ID lookups to forward unicast frames to other switches. So it's very important to understand that in FabricPath, right, end devices, servers, or other networking devices that are attached to a FabricPath cloud don't need to support or be configured or be enabled for FabricPath. They're what we call CE or classic Ethernet devices. They plug in to the Ethernet edge as simply as you would plug them into a VPC or spanning tree environment. So there's no need to, have any sort of FabricPath support on any of those end devices. And we also have the multi-destination table. A hash function selects which tree multi-destination table on which interfaces to flood traffic based upon that selected tree. So let's talk a little bit more about the FabricPath MAC table. So the FabricPath MAC table, edge switches perform MAC table lookups on the ingress frames. The lookup result identifies an output interface or destination FabricPath switch. So for example, if two devices were communicating to one another and plugged into the same edge FabricPath switch, that conversation would be classic Ethernet. We would see the MAC address in the MAC table. However, if a device wanted to communicate with another device in the FabricPath cloud, we would forward to that FabricPath switch. So we're not forwarding from destination to destination, we're forwarding from switch to switch. So now let's take a look at FabricPath encapsulation. So first here, you see a classic Ethernet frame, including its header attributes. So with FabricPath, we take that original, what we call classic Ethernet frame, and we encapsulate it with another 16 bytes of data, which includes the outer destination address, the outer source address, and the fabric tab. Right? So this particular FabricPath header is imposed on the ingress switch, as I've mentioned before. Now, some of the things that you'll note about FabricPath, we talked a lot about how a lot of the great things about Layer 3 have been brought to FabricPath to further enhance Layer 2, and we'll talk about one of those specifically. If you've used a lot of spanning tree in the past, you'll know that spanning tree fails open and causes replication, which ultimately lead to indefinite loops and cause severely degraded, if not completely broken networks when there's a problem. FabricPath introduces a TTL as part of the header. So as you see here, I actually have a TTL field inside, and at every hop throughout the network, this TTL is decremented, just like a packet being forwarded or routed via Layer 3. Once that TTL hits 0, the packet is discarded. So you'll see here that via that TTL mechanism, the loop prevention characteristics of FabricPath are far superior to that of a classic Layer 2 or spanning tree type deployment. Some other things to keep in mind about what is inside of this header, particularly in the outer destination address, we include the switch ID, so we include the unique number identifying each FabricPath switch, right? And then we also include the F tag, which we talked about earlier, and this is used for having either multiple topologies or multi-destination trees. So that's another tag here inside of the FabricPath header. Let's take a moment to talk a little bit more about FabricPath switch IDs or SIDs, right? Every FabricPath switch automatically is assigned a switch ID. These switch IDs can also be manually configured. I would highly recommend manually configuring FabricPath switch IDs in your environment. From a troubleshooting standpoint, when you're looking at a MAC address table, right, you have to track down where those MAC addresses live. So think of that concept. When we're troubleshooting FabricPath, if we've manually defined and we know our switch IDs, it will make the troubleshooting of FabricPath much simpler. So FabricPath network automatically detects conflicting SIDs and prevents data path initialization on the violating switch. So if you have an overlap, the violating switch won't be able to initialize and forward frames. All of this is encoded in the outer MAC address portion of the FabricPath MAC and MAC header. So some other important things to note, that Ingress and egress switches are used to make these routing decisions. There is no MAC learning required across the FabricPath cloud, because if you think about it, if we're simply forwarding from switch to switch, our spines don't need to know anything about the endpoints themselves. So from a FabricPath topology point of view, we can implement what's called conversational MAC learning and basically allow the scalability of our layer 2 environments to be much greater. Our spines don't have to learn about MAC addresses, and our edge devices implement conversational MAC learning to only learn MAC addresses for actual conversations or interesting traffic. So that allows for much broader east to west scalability with FabricPath. So now let's talk a little bit about the FabricPath forwarding tag, or the F tag. So the function of the F tag is detected by the type of frame, specifically if the frame is a unicast of a multi-destination. In the case of a unicast frame, the F tag identifies and selects the FabricPath topology for which the given frame should traverse. Single topology is supported with a value of 1 assigned to it. In the case of multi-destination frames, the ingress switch that receives the frame needs to identify which multi-destination forwarding tree the given frame traverses. When multi-destination traffic enters a FabricPath domain, the ingress switch uses a hashing algorithm in order to decide which F tag to program in the FabricPath header. Each FabricPath topology has 2 multi-destination trees, F tag 1 and F tag 2. Each F tag has a route switch, which we discussed earlier, that is calculated similar to a spanning tree route. The election is based on FabricPath priority and system ID. The switch with the highest priority, or system ID, when the priority is defaulted, becomes the route for F tag 1, and the runner-up is the route for F tag 2. Once an F tag is selected by the ingress FabricPath edge switch, the rest of the FabricPath core forwards the multi-destination packet based on that F tag. A multi-destination packet includes any broadcast, multicast, or unknown unicast packet. Each switch forwards the packet based on the lowest cost to the route. Once the route receives the packet, it forwards it to all the switches in that F tag except the switch from which it was received. So it implements a mechanism to avoid, much like multicast, to avoid forwarding data back to the switch in which it received from. So how is broadcast forwarding accomplished in a FabricPath cloud? So as we discussed earlier, the ingress FabricPath switch determines which tree to use based on a hash result, right? The outer destination MAC remains all ones, same as the inner destination MAC. Other FabricPath switches honor the tree ID selected by the ingress switch, tree 1 in this case, and then flood the frame on all the core ports belonging to the selected tree. Edge FabricPath switches remove the FabricPath header and flood in a VLAN. So we flood the FabricPath encapsulated frame on other core ports as well, if necessary. Last, how is unknown unicast forwarding accomplished? So again, the ingress FabricPath switch determines which tree to use based on a hash result. The outer destination MAC is set to the well-known flood to fabric multicast address. Other FabricPath switches honor the tree ID selected by the ingress switch. They flood the frame on all core ports belonging to the selective tree. Edge FabricPath switches remove the FabricPath header again and flood that within a VLAN. And then we flood the FabricPath encapsulated frame on other core ports as well, if necessary.